to our next section, which is where your project also is. We're talking about combinational logic design. So in this combinational circuit design, let us first understand what is the difference between combinational circuit and sequential circuit. Who will tell me?
Sir, output of combinational circuit only depends on the present inputs, and the output of sequential circuit depends upon present input as well as the previous inputs also.
Okay. What is an example of a sequential circuit?
Any FSM that we design. Sequence detector maybe.
No, let us say circuits that you know of already. You used them already.
Flip-flop, latch and flip-flop.
Latches, flip-flops, they're all sequential circuits. And combinational circuit?
Any basic comparator.
Normal gate.
NAND gate, abhi jo hum baat
Adder,
kar rahe the.
universal
Adder,
gates and basic gates.
yes. All these gates, they are all combinational circuits. So we'll first look at combinational logic design in this class and the next one. Then we will move to sequential circuit design in the class after that. Okay. So in terms of combinational, but in the combinational circuit design, then you have two different design styles. Most common two different design styles. We will look at other design styles also, but most common styles are static CMOS and dynamic. So static CMOS, all of us know.
Yes, sir.
What is dynamic logic?
Sir, in this logic we use a clock, and we do not use a PMOS circuit here. We use only NMOS and use the PMOS and NMOS for giving a clock above and below the NMOS logic.
Okay.
Sir, we can do it in two ways, sir. We can have a pull-up network or we can have a pull-down network. We'll be changing our output position, however, regarding that. The main issue with this dynamic logic is that, okay, advantage is that area gets reduced at first, and issue is that we'll have some race around conditions and cascading conditions.
Okay, so we'll anyways look into much more detail in dynamic logic later, but whenever we call dynamic logic, whether it is even, memory cell, for example, if it's a static memory, then you have a 60 transistor memory cell. If it's a dynamic memory, then you have dynamic RAM, then you have a capacitor on which you will store charge. So in dynamic logic, there will be some time, some input combinational state where the output is not driven by anything else, but is dependent on some charge stored on some capacitance.
So I mean the output logic will depend upon the charge stored on the capacitor at some point.
Yeah, output will be driven because of some charge stored on some capacitor. Now, if by some reason, either because of leakage or because of crosstalk or because of some other reason, that charge gets dissipated, there is no way to recover that charge during the cycle.
So, but
and you lose data, you get incorrect output.
But during the static also, the voltage, the C out what he is observing, that only will transfer the logic to the other stage.
In a static CMOS, let us say a NAND gate, if there is some noise on one of the inputs, will the output change? Okay, it may have a glitch, output may have a glitch, but it will again come back to the original correct state, is it not? Let us say I gave a small glitch on the input A of a NAND gate. There would be a small glitch on the output, but it will only be a glitch. For a dynamic logic gate, it will not get a glitch. You give a glitch on the input and you will have a permanent voltage loss at the output. Don't worry. We will see this in much more detail in probably the next class. But for now, just remember that in static CMOS, we're not leaving anything to chance. We actually always have a pull-up network or a pull-down network that is on. So the output is always driven. In dynamic logic, the output may not always be driven, and there will be times when the output is driven is only because of some charge stored on some capacitor. Is this okay?
So the capacitance drives the output, or the capacitance just defines what the output state is?
Yeah, it could be anything. So you may have a series of inverters after this capacitance. So we say, okay, the capacitance only drives the output, but this capacitance could be the output directly.
So like there could be an amplifier that actually drives some other output based on the capacity and the value stored on
Yes.
charge stored on capacitance.
Yes.
So is it something like that, or it can directly drive, let's say, an inverter without any amplifier in between?
Yeah, it can directly drive an inverter. Your dynamic gate could be input, it could be an input to an inverter. Yes.
Okay, sir.
Why
So
not?
in that case, as soon as inverter reads it, there is a chance that this dynamic logic will discharge.
Where in a CMOS gate, does the gate consume any power?
Leakage, sir.
Leakage will take years, lots of time. Gate leakage is relatively much lesser than any other form of leakage. उससे ज़्यादा leakage तो ये gate खुद कर देगा.
Okay, sir.
So good that you're thinking on those lines, but yes, I understand that you do not have the order of magnitude of these different components yet readily available to you. So you can assume this. I'm fine. So don't feel bad कि I gave you a different answer. It's fine. But that really is not that big a botheration, Madhur. Gate leakage is not really that big a botheration. So dynamic logic is still very widely used.
Okay, sir. So I can drive a static logic by dynamic output as well.
Yes.
Okay,
You
sir.
can drive static logic with a dynamic input, but dynamic logic itself has some weaknesses. We will look at that in the next session. It
Okay,
has
sir.
some weaknesses, and then you will need to take care of them. So how many of you are actually designing a dynamic AOI or OAI in your project? Put a +1 in the chat window if you are. Oh, okay, someone. Yeah. So you will see that you will have to take care of this capacitance, and you will have to check the noise immunity of your gate. We will look at various failure modes of dynamic logic. So you will need to just analyze your circuit accordingly. Okay. Gagandeep?
Sir, I was asking that if even if the DRAM cell is not a logic gate, it is still called dynamic logic.
It's called dynamic RAM cell. Yes, not logic. Dynamic.
Okay.
Dynamic because it's storing something on a capacitor, and you need to refresh it. You need to ensure that some leakage or whatever has happened, it is kind of recovered on a regular basis.
Yes, sir.
Okay. So this much you know, that in a static CMOS, there is a pull-up network and a pull-down network. And that pull-up network and pull-down network are duals of each other. All of you, even in your assignment or somewhere else, you must have seen this. You've already checked this in the in your exam also. Am I right? So pull-up network and pull-down network are duals of each other. What does this mean?
When one is on, matlab one transistor in up is on, then other is off in the bottom part.
Okay, when the pull-up network is driving, then the pull-down network will be off, and vice versa.
Yes, sir.
But how do you make a dual?
Sir, the series transistor in NMOS are parallel in the PMOS. So that is dual.
So the dual of a series transistor would be parallel transistors on the PMOS side, and vice versa. For example, in a NAND gate, you have NMOSs in series, and you get A and B. On the PMOS side, you have A parallel B. Two input NAND gate. You remember? How is a 2-input NAND gate made? Wait. So in a 2-input NAND gate, you have PMOSs in parallel and NMOSs in series. What has happened? Yeah, something is happening. So when this so this is called a dual, where the same logic is implemented. If it is implemented in series in the NMOSs, it is implemented as parallel in the PMOSs, and vice versa. Something which is implemented as parallel in the NMOSs will be implemented as series in the PMOSs. This part is clear, friends?
Yes, sir.
Okay. So if I connect NMOSs in the pull-up network, then what happens?
VT drop happens and output cannot go above VDD minus VT.
Yes, VT drops happens and output cannot go above VDD minus VT. Similarly, if I put a PMOS on the pull-down network, what happens?
It cannot drive a proper zero.
It cannot drive a proper zero. It will drive it only down to VT.
VT.
So this VT drop is something that you should always be alert about, especially when you're designing PTL logic. So what is PTL we will see, but when you're designing pass transistor logic, PTL logic, these voltage drops is something that you need to be extremely careful about. Okay, we will look into it in detail later. Okay.
So VT drop means that we should not put the NMOS in the PDN, the pull-up network.
The NMOS will have to be put in the pull-down network. Dekho na?
Yes. Okay.
When the NMOS is in the pull-down network, your output will go to 0. Otherwise, your output will only go to VTP. It will not be able to go down to full 0.
But then why they're calling it VT drop or threshold drops? I mean,
because that is what happened now. 0 was expected to be transferred here, but 0 could not be transferred. It got limited by the VT of this PMOS.
okay.
Is that okay? So I need to do something with the PPT. It kind of gets hanged every now and then. I'm not able to move there. So this is one thing that we need to be alert about, that there will be VT drops across the NMOS and PMOS when they are used to transmit VDD and ground respectively. Okay, because a PMOS cannot transmit a good ground, a good 0, and an NMOS cannot transmit a good 1. Okay. So just give me a moment. The PPT is again opening up. So when we talk of complementary CMOS, oh, you're not able to see the slide yet. Am I right? Is my slide visible?
Now it's visible, sir.
Okay. So we say that pull-up network is a dual of the pull-down network in a complementary CMOS style. And CMOS is always an inverting gate. If you want to implement an AND gate, you will have to first implement a NAND gate, and only then you will be able to implement the AND gate. Okay. So you can implement inverting gates in one stage, but non-inverting gates require 2 stages. Okay, so this much we know. I will quickly move forward. Any doubt in this one? How to make an AND gate? We've already done so much of it. NOR gate we know. NOR gate all of us know.
Yes, sir.
So if I talk of a complex CMOS gate like this, how would my dual, the PMOS network, look like? Quickly. This also I know you know.
Sir, B and C in series, sir. It's in parallel with A. And the whole circuit is parallel with, series with D.
Okay. Thank you, Vaishnav. Abhishek?
Yes, sir.
Yeah. You were saying something.
No, sir. No.
Anyone else has a different view? Or is Vaishnav correct? Is it clear?
Yes, sir.
So the dual, the PMOS side would mean that since D is parallel over here, D goes in series. A, which was in series earlier, comes in parallel, and B and C, which were in parallel in the NMOS stack, come in series. Okay, so this would be the complex CMOS gate. This is like the AOIs and OAIs that you're going to design. So how to construct a complex gate? First, design the pull-down network, and then by looking at the pull-down network, you design the pull-up network. Okay, and logical effort of complex gates. Are you able to see? We've already done this. We've already seen this slide earlier also. You remember we have seen this slide when we were looking at the first time when we looked at the G and the H thing. Huh?
Yes.
Hello. Yeah. So the logical effort of these gates can also be calculated in exactly the same manner as we did for the first complex gate. So who will give me the value of GC or GD now?
6/3.
6/3 again. What about P?
12/3. 12/3.
12/3. Great. What about now GA over here?
5/3.
What about GB?
8/3.
What are you doing? You are
We are
essentially
adding
adding the NMOS and PMOS of the gate and dividing it by 3, which is the
P
load
of the inverter.
inverter. So, and how are you able to see the way the sizing has been done?
The
Yes, sir.
equivalent resistance.
Equivalent to the resistance of the inverter.
Yeah. Okay. So we've ensured that the equivalent resistance of the inverter is same, come whatever be the case. Okay. So how do you estimate the delay of a complex gate? Like if I make a complex gate versus I make a two-stage other thing, what do you expect in terms of delay?
Path delay, sir. Path
Yeah.
delay, sir.
Yeah. So for this, the overall H, let us say, is 10. B is 1, there are no branching happening anywhere. And number of stages is 2 in both the cases. So what would be the different delays? Can you find out by using a logical effort analysis?
Sir, this is possible only if we give our output C load, right, sir?
The load has been told, na? 160 units.
Okay, sorry, sir. Yes, yeah.
So we see, okay, P is 2 plus 2. G, we know NAND gates 4/3, 4/3, NOR gate on the other side. And then GBH is something like this, and I get the delay to be 12.4 tau. I'm going quickly because this is already done. What about this one? In this case, there is a 4 input first gate and 1 input second gate. So 4 plus 1, 5. What about G? You can quickly make this gate and find out its G. You will see that G is equal to 2. F is GBH. So 20, because H is 10 over here. And what about total delay now? Total delay has increased a little, appears to increase a little, 14 tau. Then why are we talking about complex gates? If the delay has increased a little, why are we talking about complex gates?
Sir, area reduces very significantly.
Area reduces very significantly. And how do we see that? In the first case, you say that 8, 8, 8, 8, 8, 8, 8, and 25, 25, 25, 25. You just do this analysis. And what about the second one? See, the area is reduced to 36. No, sorry. Area is not reduced to 36. The second stage is 36. The first stage is 40 plus 24.
That is input capacitance, right?
Yeah, input capacitance you're saying is also a measure of area, na?
Oh, okay, sir. Yes, sir.
Is it not?
Yes, sir.
Yeah. So in the first case, what is the area? 8 devices of 8 microns each, so 64 plus 4 of 25 each, so 164. In the second case, what is the area? 16 into 4 plus 36. 64 plus 36. 100. So area has reduced so significantly. 164 versus 100. So even if delay increased by that little amount, in reality, because my area is so much lesser, the parasitics and everything will be lesser. So in fact, delay of a complex gate is also lesser. Okay. So this is one thing in reality. So this is one thing you have to prove in your projects. You know this, no?
Sir, I have a question.
Yes, Gagandeep.
Sir, if I have a gate, the complex gate which has a different G value for different inputs, so which one will I take, the worst G or the best G for the calculation of delay?
Yeah. So for calculation of propagation delay, you will take the first G.
Okay. Then contamination, the best G.
Yes. Hana?
Sir.
Now this is anyways back of the envelope calculation, Gagandeep. Final characterization you have to do on simulation.
Yes, sir.
Hana? This
Sir,
is only
in
for initial sizing. Yes, Vaishnav.
Sir, in project you were saying that okay, we are supposed to compare this both. So are we supposed to make the layout of both, or only one is enough, sir?
So how will you prove to me that area is okay? Area you can still say numbers are higher, but how will you prove to me that delay is lesser? Delay is also lesser in the complex gate if you don't make the layout.
Sir, I can say that only parasitic is small, so I'll neglect that and pre-layout I'll be doing.
How will you prove to me? How will you prove to me? Say to koi, I am also saying now.
Okay, sir. Yes, understood.
Sir, one small thing. Sir, for making the layouts of non-complex gates, so if you are cascading one NAND gate after the other, so I think metal layers would get blocked, right? Again. So metal
At most you may need one metal 2 to make those connections. Use then only for that purpose, use metal 2.
Okay, sir. Yes.
Only for that purpose. So you should be evident in that, like when you show the layout, it should be evident there. Hana?
Yes, sir.
Okay. So do you think this input order matters?
Yes,
we
sir.
discussed this. It matters.
Yes.
Hana? So where will the propagation delay be highest? Which input to output delay will be highest? A to Y or B to Y?
B
to Y.
B to Y will be highest, yes.
B to Y will be larger delay. Hai And if B arrives later, if B as an input, so see, your NAND gate is being driven by some other logic somewhere. So if B arrives later, then should B be connected to the lower NMOS or the upper NMOS?
So lower.
Upper, sir.
Then you should connect B to the upper NMOS so that what happens?
We
Overall
can
delay
drive the
of my
output
path.
faster.
Overall delay of my path reduces.
Yes.
Okay. So input order we understand matters. Then,
Sir,
okay, this we already discussed. Yes, please.
sir, why was the delay for B2 by the highest? I mean, wouldn't it depend on is it falling delay or rising delay?
Yeah, we were looking at the NMOS stack. CMOS stack में तो दोनों parallel में है ना उधर. In the
Yes, sir.
PMOS stack, both are in parallel, so the delay would be same.
I mean, sir, for rising, I mean, when the output is rising or when the output is falling, we will have different delays for A and B for different stimuli. We will get the
Okay.
worst case
So
delays.
even then, let us look at it like this. Even if it is a rising delay, it was 0 earlier. You took A to 0. So now what is the capacitance that needs to be charged? Only the capacitance on Y input, Y output. Am I right?
So what's the stimuli that you're giving?
It was output was 0 initially, so both A and B were 1.
Yes.
Now I took A to 0 so that Y charges to 1. That is what you want to see, na? Rise delay.
Yes, sir.
So now what is the delay? What is the RC? CMOS 2 and output is
Yes, in this case, B will give the worst case in that case.
okay. So let us say the output is to fall.
Yes, sir.
Then what is the worst case?
This means that
If A was already 1 or if B was already 1. The
yes,
other
sir.
input now goes to 1.
Yes, sir.
Which one is more delay?
So if A changes, then
If A was already 1, then what has happened?
so now A's
But X is
capacitance
also charged to
has
VDD.
plus-
X is also charged to VDD. Or VDD minus VT, in fact.
Yes, sir. Okay, sir. So in both cases, B is the worst case.
Yeah.
Okay, sir.
Is that clear?
Yes, sir.
Sir, just to add upon this,
Yeah.
the input order also matters because if I consider a function y is equal to a into p plus c, then we'll have, if we attach the parallel connection of V and C to the output, then we'll have more parasitic capacitive loading at the output. So that has to be connected to the ground, whereas A should be connected to the output, right, sir?
Yes. So मैं तो कह रहा हूँ Ranjit, what I'm saying is that even in a simple two input NAND gate, even there, the input which is closer to the output should be the one that is arriving late.
Yes, yes, sir.
Even in a simple circuit like a NAND gate, I'm telling you this, that order matters.
Yes, sir.
In a complex circuit, you're absolutely right. Bang on. Output definitely matters.
Yes, sir.
Okay. All of us understand why it matters? Any questions around that, please?
Yes, sir. So I mean, what exactly was we discussed? I was not able to get Ranjit was mentioning.
So Ranjit was mentioning that if it's a complex gate, it matters still more. Because then that will change the intermediate, like suppose if it's A and B parallel and C in series in the NMOS stack. So if I put C above on Y, if Y is directly connected, like the series and transistor C is connected to the output and A or B are in parallel connected to ground. Then there would be one delay. And if I have a different structure where A and B are in parallel connected to Y and C is in series connected to ground, that will have a different delay. For different, like there will be different delays for A, B, and C to output in these two structures. And you have to design appropriately. Experiment, you will see.
So, and you were saying that the input closer to the output should arrive the latest, right?
For a NAND gate, yes. Whichever input has shortest delay should be designed to be arriving last in your path. In this particular example, if you know that there are two inputs A and B, if you know that the first input is arriving faster, that first input should be connected to B.
So, but in
Is that
that
okay?
case, if you're considering the propagation thing, so the capacitance between these two shade that will discharge if it arrives fast, and
Yeah.
will not get the propagate, will not get the worst delay then basically.
Yeah. We're not characterizing now. Now we are designing a path. You want the delays to reduce in a path, na, Raghav?
Okay, fine, okay.
We have graduated from characterization to designing.
Okay, so now we are ordering the input such that we get the least delays.
Least delay in my path. Just
Okay.
like for logical effort, the intent was to get least delay and least area in the path.
Okay, so but then in that case, we will also be the specification will also specify ki how the signals are arriving, right?
Yeah. So, for example, if I ask you to make an adder, you will know now which signals will arrive first, which will arrive late.
Yes. Okay.
You are a designer. It is not about designing one gate, it is then designing a path. Okay.
Yeah, got it.
Similarly, you can actually make gates asymmetric so that the non-critical input may have higher load. For example, in this case, reset bar has higher load and a critical input A has lower load. So overall load of this gate would increase, but the delay for signal A would reduce significantly. Are you able to see this? See, my A signal was arriving late. A signal is on a critical path. Reset is something which, like sleep pin or something which already is there, static signal already there. So you let the reset bar come, and then for A, because that is the actual critical path, the critical input, you have reduced the delay very significantly by reducing the size of the NMOS. Are you able to see this? So if you're making full custom paths, then you may want to design asymmetric gates also so that you reduce total delays. Are you with me? Any questions?
And this critical thing was not clear, like the path of A.
Critical path for over here would mean path which has the largest delay. So A was coming from a path which had the largest delay.
Yes, sir. Okay.
A was coming last. So I wanted to put A closer to the output. That I already did.
Yes.
Now I want to improve performance further.
Okay.
So what I did was I reduced the load on A also, so that A can arrive a little faster.
But
And I increased the load on reset bar.
Right. Okay.
Sir, how did you share the load between A and reset, sir?
Share the load. I reduced the load of A.
Okay.
I reduced the load of A, so resistance of A increased. I then said, okay, let me increase the size of B so that I still get the same equivalent resistance as an inverter or a regular NAND gate.
Okay, sir. Yes.
Okay.
Hello.
Gagandeep?
Yes, sir. Sir, this is fine that you reduce that load for A, but sir, now Y node will also take more time to discharge to the 4x3 NMOS, which could be a faster discharge to a 4 NMOS.
So wait. Look at it like this. Had it not been 4x3, I would have designed two NMOSs of resistance of size 2.
Yes, sir.
So my overall resistance would have been R.
Okay.
Now, what is the overall resistance now? 3/4R plus R by 4. It still is R.
Okay, so you have upsized the reset also. Fine. Yes.
देखो ना, otherwise it would have been 2, na?
Yes, sir.
In a
Yes,
regular
sir.
NAND gate, you would have put both the NMOSes to be sized 2. So the overall area you have increased, but the delay you have reduced. Huh?
Yes.
And you could actually also have symmetric gates designed. So you had 2 NMOSes, each was 2 microns, but both the inputs were coming randomly at same time. So you said, oh, I want to give equal delay from A to Y and B to Y. So you make a symmetric gate like this. 1 micron of A is closer to the output, 1 micron of B is closer to the output. The other 1 micron is farther from the output. Are you able to see this? Any questions on this also?
So we are just reducing the load here, right?
We've not reduced the load over here.
Then
NMOS
what-
B was supposed to go to a NMOS which was total size 2. It is still going to total size 2.
Yes, sir.
I've just rearranged the NMOSes in such a way that equal strength of A and B NMOSes is closer to Y and equal strength of A and B NMOSes is closer to ground.
Okay.
That's all I've done. Okay. And you can actually also make skewed gates. I'm just taking this through because this is kind of very simple and the last slide on CMOS. Okay. You can also make skewed gates if you want to say that I want to favor rising outputs over because for example in an adder carry equal to 1 you want to bring up faster. Carry goes to 0, you can bring it down later also. So you know that one path is faster. Or let us say even a comparator, a 20-bit comparator. So XOR gates connected to one another. You know that falling would anyway be fast. Rising is something that will take time. So I want rise to be faster. So you can actually skew the sizing so that when you skew the sizing, what happens? Your transfer characteristics shift to the left or to the right. I'm not able to draw this on my screen. I'm surprised why. So questions here. What happens when I skew? Are you able to see the benefit of skewed logic? Any questions around that?
Sir, but this brings an overhead with noise merging being affected, right, sir?
Yes. Yes. So even, when I went to asymmetric gates, noise margin could have been impacted.
But this increases the effect on noise margin with a greater
Yes.
extent, right, sir? Because any
Yes.
glitch can change the output at any instant.
Yes. But for my preferred side, I get a faster output. For example,
Yes.
if there is a signal which is continuously precharged to 1, and I want to sense when it falls.
Yeah, this skewed
As
gates
soon as
can
it
be
starts
used.
to fall, I want to sense it. Then I want to have this kind of a skewed logic.
Yes, sir.
Hai na?
Yes, sir. Yes, sir.
Okay.
So actually, I'm not able to get this concept. Actually, can you this of skewed gates? Like what exactly we're doing here? Earlier, I was able to get earlier we were reducing the load on the
Yeah.
critical path. But
So now let
we
us say that I am in the first gate. I am interested in output going to 1. Output falling, I'm not bothered about. In my state machine, output going to 1 has a very significant role to play. We're talking about a state machine here, where one transition is more important than the other.
Okay, the
So
charging basically is more important for me than discharging.
yeah, let us say that Y rising is more important than Y falling in the first case. So what happens now? The total load of A has reduced. Are you able to see this? Total load of A has reduced. Can you see this? Instead of 3, that is 2 of PMOS and 1 of NMOS, I now have 2.5 total load. Hmm? Additionally, I said that because this load has reduced, A will now transition faster, and therefore my output will also transition faster. I've also skewed. So NMOS will now have lesser on current, and I will be able to take Y to one level much faster. So two ways I'm benefiting in terms of rising of Y.
So one was that the load was getting reduced, so transition faster. But what's the other benefit you?
So in the transfer characteristic, I have shifted this. Because I have made NMOS smaller than the strength of NMOS smaller than the strength of the PMOS. So my switching will happen faster, earlier, at a lower value of. In fact, at a still higher level of A, I will start to have Y rising, because NMOS will not be able to conduct as much current as the PMOS will be able to provide. You remember the skewed inverter wala cheese?
Yes, I mean that shift, that curve shifts left or
Exactly,
right.
that's it. That would happen, na?
Yeah. But that was impacting so the noise margins. I mean,
That is also impacting the delays. That is what I'm telling you.
Okay. Yeah. Yes, sir.
So how will
Okay.
that impact the noise margin? Because it will just shift but not change the slope.
Now a very small disturbance on A will also cause output Y to toggle.
Why? I mean, so we define noise margin as 45 degrees slope for that around region C. So that region C is only shifting, but it is not
Yeah.
changing its slope. So why is
एक मिनट 45 डिग्री स्लोप तो हमेशा ही कभी ना किसी हमेशा ही किसी ना किसी सर्किट की आएगी ना.
Yes,
So
sir.
what was the noise margin? The noise margin was 45 degree slope wala point to 0 or 1.
So can you repeat that, please?
It was the point where you get that 45 degree wala slope. Just let's go to the whiteboard. We were saying that we said this point and this point.
Yes, sir.
They define my noise margin points. So what is the noise margin? This is the noise margin, na? So if I have shifted this curve here, this 45 degree wala point has shifted here. So the noise margin has reduced, na?
Okay, got it. I understood noise margin wrong.
Okay.
Yes.
So when you use skewed gates, the noise margin gets degraded. Okay. And you could have high skew, low skew, but you could design both the sides. Okay. So we will stop here. We've covered these concepts today. We talked about static CMOS, where pull-up network is a dual of pull-down network. We talked that complex gates are denser, they are low power, and they are equivalent speed. We've talked about the importance of input orders, symmetric and asymmetric gates, and also skewed gates. Next class, we'll start to talk about different logic styles, ratioed logic, pass transistor logic, and other styles. Okay. So we'll close the class today. It's already beyond the class time. I know this. I'm sorry for that. But we had more discussion, and that was an important discussion. So we didn't stop that there. Okay. Thank you guys. All the best. Stop the recording.
So just before even when we were when you're saying that the input ordering, when you explaining the input ordering concept, we were basically more focused towards, we were basically in the concept of the critical path, critical delays. We were discussing the input ordering.
Yes.
But when we were discussing the skewed one, it was in the context of like favoring, like if that.
Yeah, now you're talking about critical path, not just in terms of path, but also in terms of which direction we want the transition to happen. We're being very, very specific.
So like it will be over and above that discussion. Okay.
Yes. Okay.